Today I wanted to revisit the WHAS 500 script and finish it up. There was just a little bit left for us to do. But briefly reminding us what we did, with these data we looked at a routine for building a model. And so, big picture, if you have a spreadsheet full of variables, you have maybe one response variable and some predictor variables, and you're interested in what should a model look like relating the response variable to your predictor variables, a good place to start is look one by one at the predictor variables. Predictor variables relative to the response variable. What does the relationship seem to be, considering each one separately? Using one-by-one assessments, pick some of your covariates to consider as part of a multivariate model. And you could consider then if any of the covariates that were selected one at a time could be removed from the multivariate model. If, for example, some of the covariates are highly correlated with each other, you arguably don't need all of them. So suppose there was just two covariates that were really highly correlated with each other. They're essentially telling you the same information. So unless there's really good reason to leave those two both in the model, you would arguably be better off without them both in the model. So if you had two covariates that were very, very highly correlated, you might consider removing one of them and just keeping the other. But more generally, just because individual covariates look like they have a substantial relationship with the response, when considered one at a time, when you put them all together into a multivariate model, we might see that some of the relationships don't hold up once we're adjusting for other things. So we considered initially which variables go in the model. We should also consider the nature of the relationship between a response and any covariate that's included. Remember that whenever you do a regression model, response equals beta 0 plus beta 1 covariate. That beta 1 is being interpreted as a slope parameter. It's a mean change associated with a 1 unit increase in the covariate. So that there's an assumption there that that covariate is linearly related to the response. And you want to check that. In an arbitrary regression model, we've made pictures of residuals versus the covariate and looked for any systematic patterns to those. With a Cox model, it's not as easy to draw, or residuals are not as easy to get. So what we did here was to kind of use an ad hoc approach to bin a numerical variable and fit separate means to each bin and ask whether those estimates are roughly linear. But big picture, you're interested in, you want to make sure that the assumptions of your model are reasonable. Interactions, should there be any? Which ones should there be? Ideally, you would have domain expertise that informs the choice of any interactions. Sometimes interactions are of primary importance. Depending on the study, it may be that you're specifically interested in doing inference on an interaction. I could give my female mice estrogen in their diet. I could give female mice a carcinogen inhibitor. Wonder what happens if I do both. Is it better? Is there synergy, so to speak? Is there an interaction where having both treatments is especially beneficial? That'd be a case where you're specifically interested in doing inference on an interaction. And then the other check that we need to do with Cox models is with respect to the non-proportional or the proportional hazards assumption. For every covariate in the model, the Cox model is making an assumption. So the Cox model is that the log hazard at time t for an individual with covariates x and for beta coefficients beta, this equals equals the log baseline hazard plus x beta. So remember, the Cox proportional hazards assumption was that the hazard could be factored into a piece that depends on time but not the covariates. That's what we call the baseline hazard. And another piece that depends on the covariates but not the time. So for every covariate in there, let's say, I'll keep it as is, log baseline hazard plus, so we would have a beta 1 x1 and a beta 2 x2 So every one of those covariates has a beta coefficient, but it does not show up in the baseline hazard. So for every one of those covariates, we are assuming that the betas do not depend on time. The effects of the covariates do not change with time. If we have evidence that the effects do change with time, then we have evidence against the proportional hazards assumption. So I'm going to show you today two ways to assess that assumption. The easy way is to use this built-in function in R, Cox ZPH. And the way it works is you provide a fitted Cox model, and that's it. It's going to give us p-values for each of the covariates in the model. So let me come back up to the top here and load the data and run all this interim code so that we can run the check at the end for whether proportional hazards hold. This ended up being our final model. Actually, this one did. We went ahead and put an interaction in the model. So we ended up with age, heart rate, diastolic blood pressure, BMI, gender, CHF, which I don't remember what that is, and then an interaction between age and gender. We added the interaction because we tentatively added the interaction, and we noticed that there was a small p-value for that term. So it looks like there is a substantial interaction. Again, I don't like using p-values, but with some models, like the Cox model, it's a little bit harder to just make pictures to make these choices. So we'll go ahead and pick this model at the end here. Fit is that Cox model with the covariates we just mentioned and an interaction. And then let's use this built-in function, Cox.zph. And we get a p-value for every single covariate, and we get an overall p-value for the model as a whole. So I don't know the formula for how they come up with that p-value at the end, but it's in some sense a combination, an overall assessment of whether proportional hazards holds with respect to this model. If we look at the individual p-values, there's only one that is close, that's age. So we have mild evidence, moderate evidence maybe, of a non-proportional hazard with respect to age. Overall, the model looks like it's making reasonable assumptions. I will show you today how to make a picture to assess these kinds of things. And also, probably not today, but coming soon, I'll tell you about alternatives that we can use if we're trying to fit a Cox model, but it looks like one or more of the covariates does not satisfy proportional hazards. There is a couple of tricks that we can do to enable that. There is also a different type of model, a different type of regression model, not Cox model, that allows regression with survival data that I'll show you later this week, called an accelerated failure time model. But that's a parametric model. Cox proportional hazards is called semi-parametric, in the sense that we're not specifying the distributional form of the event times, but we are specifying a kind of strict relationship, and that is the proportional hazards assumption. So it's called semi-parametric. Okay, so let me go to a new script. I just downloaded it today. It's on eCampus. It's called the Heart Data script. And I have a picture in here for a rough check of proportional hazards. Before we go here, let me just remind us from the notes. Let me come over to where we were talking about proportional hazards assumption. We said a couple of things about relating the survival function and the hazard function. That's useful because once you fit a Cox model, it is handy to be able to use the model to create covariate-specific survival curves. So if I could fit this model that has covariates for age and gender and all these other things, if I could then ask, according to the model, give me a survival curve estimate for 20-year-old males of this particular comparison group. So we can do that through this relationship here. The survival curve is equal to e to the minus cumulative hazard. The cumulative hazard is just like a cumulative distribution function. It's an integral from the left up to t of the hazard function. So we can relate survival to hazard. Here's where the estimated survival curve can come out from the fitted model. If we have an estimate of the cumulative baseline hazard, which we can do in a non-parametric way, I'll show you an example if we have time, then we can put that together with the fitted covariates or the fitted coefficients from the model and get a survival curve estimate for a given choice of covariates. I'll come back to this. I did want to say something about this, but I'll come back to it. In order to check the proportional hazards assumption, the key is that the effect of covariates does not change with time. So the effect of every single covariate in our model is constant with respect to time. That means effect, that means hazard ratio. Betas are log hazard ratios, so e to the betas are hazard ratios. We're assuming that there's a constant hazard ratio for comparing, say, males to females across all times, across all event times. So going back to the relationship between survival curve and cumulative hazard, what we can do is, suppose we have one covariate X. We're going to consider just one for now. One covariate X that is binary. It's either 1 or 0. That might be treatment group and control group. Then using this relationship, we can estimate, say, Kaplan-Meier curves for x equal 1 and x equals 0. Actually, we don't need to even look at the model to compute these Kaplan-Meier curves. we could just go get the survival times and censoring indicators for everybody in x equal 1, and same thing for everybody in x equals 0. So I can compute survival curve estimates for these two groups. Now, using the relationship between survival and cumulative hazard, because survival is equal to, or at least the estimated survival is approximately equal to e to the minus cumulative hazard, then if let me write it over here, we have that S of t given x and beta is equal to e to the minus hazard function. So if I have a Kaplan-Meier estimator, S hat, I can say that that's an estimate, at least, of this quantity. Then if I log transform, let's log transform the Kaplan-Meier curve. That gives me approximately minus the cumulative hazard. And if I log transform the minus log transform of the Kaplan-Meier curve, we have that this is approximately the log of the cumulative hazard. So if you have a PDF, like a density function f, and you have a CDF, capital F, so f of x, and capital F of x is the integral from the left up to x of the PDF. That's what the definition of cumulative distribution function is, integral from the left. Then we also have that f of x, this is a basic result from calculus, fundamental theorem of calculus. You can recover the PDF by differentiating the CDF. What I have at the bottom of the slide here, log cumulative hazard, the log cumulative hazard, x and beta, is equal to log of integral from 0 up to t of the hazard. And according to the proportional hazards assumption, this is equal to integral 0 to t. The proportional hazards assumption says that that quantity is equal to a product of baseline hazard times e to the x beta. So that e to the x beta can be pulled out of the integral because it has no t in it, which means this is log of integral 0 to t h0 of t dt plus x beta. I could pull that e to the x beta outside of the integral. Then it's a log of a product, which is the sum of the logs. So this is just some quantity, log capital H0 of t, we could call it, plus x beta. So if we have like one covariate, say, that is binary, 0 and 1, 0 for control, 1 for treatment, then what we can say is that the survival curve estimate at a given time t when x equals 1 is approximately equal to this log baseline hazard plus beta 1, we'll call it. Forget about any other covariates. We'll just say, really simple case, we have one covariate, it's binary. In this case, for the x equal 1 group, we have this as the estimated relationship between Kaplan-Meier curve and coefficients from the model. And we could put a hat on this in particular. So then the Kaplan-Meier curve for x equals 0 is same first piece, but now it's 0 because this is x equals 0. Not capital S. This should be log minus log capital S. Log minus log. Log minus log. Okay, so what this means is that if we compute a Kaplan-Meier survival curve for x equal 1 and another Kaplan-Meier curve for x equals 0, and then if we draw the log minus log survival curve estimates, if we draw these next to each other or against each other, what we should have is that the top one, the y-axis, is equal to the x-axis plus some constant. Over all the times, if proportional hazards holds, what we should see is roughly a straight line shifted from equality by some constant amount. So roughly speaking, all we really care about is there a straight line? If I do Kaplan-Meier curves, binary covariate, Kaplan-Meier curves for x equal 1 and Kaplan-Meier curve for x equals 0, log minus log transform both of them and plot them against each other, we're looking for roughly linearity. If there's linearity, then that says that the effect is roughly constant with time. Let me show you one example of actually implementing this. It's easier to implement than it is to describe what it is. So let's go to the heart data real quick. These come with the survival package, and let's take a look at what they contain. Yeah.
So is it possible the intercept for the line is 0?
It is possible that the intercept for the line is 0.
Then the beta 1 has to be 0, right?
That would be indicative. That'd be what you would expect to see when you had a beta 1 that was not statistically significantly different from 0. I wouldn't recommend making this picture to make inference about beta 1. That's not the point of this picture. We can test whether beta 1 is 0 by looking at the p-values in the output or a likelihood ratio test. So the main interest here is, does the proportional hazards assumption look reasonable? Okay, we have survival time data for people. Let me look at the help file. The data set file name is called HEART. So we have survival times of patients on the waiting list for a heart transplant program. We have several covariates. We're going to look at, I think, follow-up time. That's the time under study. And censoring indicator, foo stat, follow-up stat, dead or alive, is our censoring indicator. Then we have a covariate for prior bypass surgery. We have age. Mismatch scores. So these would be some kind of quantification of how far from perfect was the match between a heart transplant that you already received and what it should have been to perfectly match with your makeup. Actually, we have just the heart data. These data are here in multiple formats, which is a little confusing. So there's one format that is, I guess, less processed. And there's a couple of formats that are more processed. And the heart data set that I'm going to play with right now is the more processed version. We have start and stop times of observation, as well as censoring indicators. And then we have age, year of entry into the program, prior bypass surgery, did they receive a transplant, yes or no? So let's come back to the script. And I'm going to pull out the survival times. I'm just going to use the stop variable as the survival times. We actually have a start and a stop, but I'm going to only focus on stop times. Stop time, the start and stop is time of observation, but I think stop is with respect to a common start point. So I'm just going to use stop as our response time. And then delta uses the event variable, and we'll keep track of age, surgery, prior transplant surgery, or prior, bypass surgery, and transplant, yes or no. So we have 1, 2, 3 covariates. Age is numerical, surgery is binary, and transplant is binary. Might as well run this. This is an assessment of ignoring the other covariates. Let's look at survival prognosis by transplant status. So among those who got a transplant, what was their survival outcome like? And among those who did not get a transplant, what was their survival profile like? So there's very obvious difference in survival prognosis. Let me see if I can figure out which curve is which. So for transplant equals 0, these are people who did not get a transplant while under study, while they were in our study. Time 340, they had an estimated survival of about 0.06. So those who did not get a transplant have much worse survival prognosis in this example. I figured that out by just looking at the biggest event time for the non-transplant people. The last event was at time 340, and at that time the survival probability dropped down to 0.07. So there's 340-ish, and that's 0.07-ish. Transplant 1, we had individuals who lived out 1,000 days, 1,400 days even. But again, that's not with respect to the covariates. We have not adjusted for age or bypass surgery. So let's try doing that in a second. Okay, before we do it, here is our effort at checking the proportional hazards assumption. Surgery and transplant are both binary. So the breakdown here that I wrote on the whiteboard applies. All we need to do is compute survival curves. Kaplan-Meier will work. Kaplan-Meier survival curves for transplant yes and transplant no. Do log minus log transformation, plot them against each other. Does it look like a linear relationship? And then we need to do the same thing for surgery, prior bypass surgery. Kaplan-Meier for yes, Kaplan-Meier for no. Log minus log transformations, do they look roughly linear? So what I'm going to do is use the serve fit function to fit separate Kaplan-Meier curves for each category defined by these two binary variables. If I say serve fit, capital serve, tilde, and I give it two covariates separated by a plus sign, we're going to get all four survival curves. I broke down the number of event times by category. For surgery equals 0 and transplant equals 0, there were 22 individuals. For surgery equals 0 and transplant equal 1, there was 35. And there were very few in the surgery equal 1 group, relatively few. So there was only 3 who had had bypass surgery but no transplant, and there were 6 who had had surgery and a transplant. So with so few observations in this category right here, trying to make a picture like this one is not really going to work out very well. With only 3 points, it's going to be hard to see any kind of real pattern that you would believe is persistent. So what we can do is, for example, we could compare, let's see what I do here, 1 to 22, and then this is 58 minus 23, 35. Okay, so I'm only going to look at these top 2 categories because I don't think there's enough observations in the latter 2 to even make a picture. These first 2 categories, I can use them to assess proportional hazards with respect to transplant. The 22 have transplant 0, the 35 have transplant 1. These are the times and the survival probabilities for those 2 groups. No transplant, no surgery but yes transplant. So we can now make a picture. Here is time on the horizontal axis and log minus log survival probabilities for the no, no group. And then I'll add line segments for log minus log of the survival probabilities of no, yes. If proportional hazards with respect to transplant hold, then these curves should be roughly separated by a constant amount. If you look from the right, most of this through here looks reasonable, separated, that looks roughly constant. It gets harder to tell as you come through here, but maybe these are actually not too different from up here. It's just harder to tell because of the shift that it took.
You subtract them and then draw them.
That'd probably be good, yeah. Let's try doing plot TT 0, 0. All right, but to do that is going to be challenging because they don't have events at the same time points, so I can't just take the survival probabilities from this one and subtract those because they won't line up. I wonder if there's an easy way to get that done. Let's try TT. Let's hold on to all the unique event times. So I'll say unique, concatenate all the event times from the 0, 0 curve and all the event times from the 0, 1 curve. And then let's see if we can get predicted values. I'd have to think a little bit about how to do it, but I think we could do it. We would just need to somehow get out interim points on the survival curves. Let's see if I can figure out how to do it for next time. But it is kind of hard to tell because of the tailing off to the left. But it is arguably getting a little bit tighter as you come down to the left. But I've seen much worse pictures. So I don't feel all that bad about assuming proportional hazards. If these were crossing each other, that would be clear evidence that they are not proportional. In other cases, you'll see them coming together over at the right hand of the picture where it's easier to see. What we can do is use that Cox ZPH function. So we could try, I'm going to do that down below. Right now, all I've done is assess the transplant covariate. Let's also consider the age covariate. So with age, it's a little bit more challenging to make this picture because age is numerical. If you have categorical, then you can express this relationship in terms of log minus log plots that should be separated by beta coefficients. But with age, for example, age is numeric, so it's not beta 1 and 0. It would be like beta 1 and, so we would have like beta 1 hat age and we would need beta 1 hat for age minus 1 in order to have these be separated by approximately beta 1. So what we need to do with a numerical variable is compute, what we can do is bin age into multiple categories. The easiest way to do binning is to use 2 categories, although that's probably not optimal. We'll do 2 categories because it's the easiest way to do it in this case. So we're going to bin age by whether or not it is less than or greater than minus 0.25. That's approximately the sample median in these data because these data were median centered for age. age is actually age minus 48 years. So minus 0.25 is approximately the sample median. So what I'm going to do is, like we did above, I'm going to create a categorical variable, yes or no, is age less than minus 0.25. And then create two Kaplan-Meier curves, pull out the times and survival probabilities for each, and then plot the two minus log, or log minus log functions. So this one's clearer, easier to see that there's a change in the distance with respect to time. So it looks, based on this picture, like there is not proportional hazards with respect to age. Let's go ahead and come down to the bottom and use the Cox ZPH function. So I'm going to go ahead and fit the Cox model that has all the covariates in it that we've considered, age, surgery, and transplant status. And then we will pass that in to Cox ZPH. Let's see what it says. So age, for some reason, did not show up as a problem, but transplant did. That's interesting. It might be that we really need to do the differences instead of just making this picture. It could also be that by having these other variables in the model, it changes the patterns that go with this variable. The ideal outcome would be to run this function and see maybe a small p-value for one of them and make one of these pictures and see a consistent story that backs up the p-value. Because that suggests no problems whatsoever with respect to age. So let me figure out how to make this picture with the difference with the differences and see if it looks any different than it does here. When in doubt, I would say go ahead and use Cox ZPH. Making the pictures is handy because it's easier to see why we're accepting or not accepting, easier than just seeing a p-value. So the problem with just looking at a p-value is that you don't know, what's the nature of the discrepancy. Is it a big discrepancy, or is it not worth worrying about, or what? All right, more on that next time. Let me say something while we're here. This is relevant to your homework. When we fit the Cox proportional hazards model that had age, surgery, and transplant in it, if I say summary CPH fit, then if you wanted, say, a confidence interval, let's say we wanted a confidence interval for the log hazard ratio comparing two individuals who differ in age by 1 year holding transplant and surgery constant. So among those with the same transplant status, same prior surgery status, let's compute a confidence interval for the log hazard ratio comparing two individuals who differ in age by 1 year. All that language, all that's doing is describing beta coefficient for age. That's the interpretation of the beta coefficient for age. Mean, well, not mean, but log hazard ratio comparing two individuals who differ by 1, holding everything else constant. So if I wanted a confidence interval for the beta coefficient that goes with age, what I would do is estimate plus or minus some critical value, and we can use, with a reasonable sample size, we can just use the standard normal, times a standard error. This is the standard error of the coefficient. So this would be confidence interval for log hazard ratio. Suppose we wanted a confidence interval for log hazard ratio comparing two individuals who differ in age by 10 years, holding transplant and surgery constant. If 0.05889 is the log hazard ratio comparing two individuals who differ by 1 year, then 10 times that would be the log hazard ratio for a difference of 10 years. So if I want to change from a 1 unit change to a 10 unit change, my estimate is just 10 times the beta coefficient. And the standard deviation of 10 times a random variable is just 10 times the standard deviation of the random variable. If we have a random variable y with mean mu and variance sigma squared, the variance of a constant times y is a squared sigma squared. So the SD of AY would just be A times the SD of Y. This is then a confidence interval, 95% confidence interval for log hazard ratio comparing two individuals who differ in age by 10 years, holding everything else constant. And suppose we then wanted a confidence interval for not the log hazard ratio, but the hazard ratio for the same exact comparison. What we can do here is take this confidence interval for the log hazard ratio and just exponentiate it. So I think I asked you something in your homework about give me a confidence interval for a particular comparison. And you can get those by starting with a confidence interval for the coefficient itself. Coefficient estimate plus or minus cutoff times SE of the estimate. If you want to change the unit difference, you just multiply the estimate and the standard error by that number. And if you want to translate that interval for a log hazard ratio to a hazard ratio, you can just exponentiate the interval that you got for the log hazard ratio. Log hazard ratio for a unit of 10 difference does not include 0. 0 is the kind of null value on the log hazard ratio scale. And so equivalently, the interval for the ratio does not include 1. They're both telling us there's a statistically significant difference in the hazards. All right, we are out of time. We'll tidy up some more stuff with survival data next time. I have some more kind of specialized topics to discuss in the context of survival data. What can we do when there is not proportional hazards? What are some alternative types of regression models when we don't like the proportional hazards model? Yeah, that's basically it. Okay, so see you Wednesday.